And we begin the last unit of IB mathematics. Unfortunately, we're not finished, like I said. We will still have to go back and redo the calculus that we quote unquote learned in fourth quarter of last year. And we will have to finish the calculus that we didn't get to because I was only allowed to assign you 2 things per week. So we actually have a lot of calculus to still do this year. That is unfortunate, but this is going to be the last unit for a little while until sometime in, I'd say, mid to early January. This will be the last unit because it's IA time after that. But this unit is all about normal distributions. Now, the textbook doesn't call it this, but what does it mean to have normal distributions? Well, last chapter, unit, was about binomial distributions, right? But it was specifically called discrete random variables. The normal distribution is continuous random variables. That's the difference. So this unit, we're talking about continuous random variables rather than discrete. So now we're talking about lengths and heights and weights and things that can be measured instead of counted. Okay. Bell curves. Everything's about the bell curve. The curve y equals f of x, which is called a normal curve, which you're looking right there, is symmetrical about the vertical line x equals mu, the mean. Mean is right in the middle. The normal curve, the bell curve, is symmetric around the mean. As x goes to positive or negative infinity, the bell curve, the normal curve, is going to approach the x-axis, so it's going to approach 0. Scroll down. All of your values for y are positive. I hope that's obvious. And because all probabilities have to add up to 1, here's some stuff that you probably don't understand because calculus from last quarter, quote unquote, last quarter was a train wreck. But what that says right there is the area under the curve adds up to 1. That's what that says. So when you are finding probabilities, you are actually finding the area under the curve up to a certain point. This says if you add up all of the area from left to right, all of it, it adds up to 1 because the probabilities of things happening add up to 1. More scores for the normal distribution, more scores are closer to the mean than they are further away, and they result in a bell shape. And what's neat is bell shapes happen naturally. This is not something that people invented to be fun. Your packet is in the absent binder. There's a science museum up in Tennessee that I used to go to every single your year 2 absent binder. There you go. There's a science museum up in Tennessee that I used to go to every summer as a young nerd, and they had this thing where it was like a hopper, and it had, we'll say, hundreds of balls in it, hundreds or more of balls, and it had a bunch of, at the bottom of it, you press a button and they would all fall, and along the way they would hit pegs. Okay. Now at the bottom there was just a bunch of plastic slots, and everything was clear so you could see through it. Just a bunch of slots, right, of whatever height. You press the button and the balls would fall. And when they were all done ping-ponging around off of the pegs and landing in slots, they'd formed a bell curve. And then, you press another button, it would suck them out, bring them back to the top, refill the hopper. You could press a button again, and they would all fall. And after they ping-ponged around off the pegs, they form a bell curve. So these things occur naturally, just random chance, but they happen naturally, which is really neat, actually. So this is one of those times where we use math to describe something that occurs naturally. Mm-hmm.
It could all fall on one side.
It could, yeah. So this is actually it's more of an average of all the outcomes, yeah. So do they always make the perfect bell curve? No, but the bell curve ends up being the average shape.
All right.
Yeah, so it's because it's an average, like you said. Technically, they could all fall in one slot. There is a statistical chance, but it's very, very rare. The average shape ends up being this. So for a normal distribution with mean, mu, and standard deviation, that little sigma, you see up until now, you didn't really know what that was used for. The percentages between the random variables land like this. And unfortunately, for some people, these are numbers you have to memorize. Memorize. It's nothing to understand. You memorize them. So for individuals in the class that have baked away their memory cells, I'm sorry, but you do have to memorize these. IB requires it. But here's what it says. You've got your mean right here, your average right there, mu. You could go one standard deviation to the right, so that would be mu plus sigma, or one standard deviation to the left, that'd be mu minus sigma. Because the thing is symmetric, the spaces between those first two vertical lines are the same. There's roughly 34, and these are more specific, but there's roughly 34% here and roughly 34% here. So when you find plus or minus one standard deviation, you're supposed to be finding about 68% of the data. My curve that I use to curve your tests, 68% of the scores fall within one standard deviation of 75%. That's why I made it that way. I made 75% average because the lowest score you can get is a 50, the highest scores you get 100. I said, fine, 75 is the mean. And I made sure that plus or minus one standard deviation roughly was 68%. Now, I was a little more fair than that because, to be honest with you, that would mean that only like 7% of people get an A. So I started with the bell curve and I thought, let me flatten it out a little bit and help some people out. But that was how I started it. That's how I developed it. So thank you, IB Math, for teaching me how to do that. What you're supposed to be realizing and seeing from this picture is that every time you go another standard deviation away from average, there's less and less area under the curve, which means there's a less and less probability that that occurs. The next bracket you can see is about 13.5%. So that's more of a classic number, 13.5%. Both there and here. So what are these, and then so on and so forth. And then you've got another little 2%, and then you get this like 0.13%. And notice that it doesn't say plus 4 standard deviations or plus 5 standard deviations. You know why? Statistically impossible. So for those of you that like to play video games, guys, you ever wonder how the aimbots get caught? How they get blocked, how they get banned, how they know that you were cheating? Because it's a machine that decides if you're cheating or not. It's not people. They report you. Other players report you because they suspect you're cheating, and then another computer quickly checks your shots in the games. Let's just say you're playing like CSGO or something like that. And if the number of headshots you make is something like 4 standard deviations above average, they know you're cheating and you get banned because that's statistically impossible. So this math is used all the time. By the way, Einstein's IQ was something like 5 or 6 standard deviations above average. He was statistically impossible. I think it was 5 or 6. It might have been 3 or 4, but the point is it was ridiculously high. Like, a higher IQ than over 99.9% of the people on the planet. Something like that. Okay. So not only do you need to know the spaces in between, the 34, the 13.5, then we call that like 2 and then 0.1 or something like that, or like 0.15. We try to make the numbers prettier than they are for you to memorize. You also need to know how much is covered. So to the left of mean, that's exactly half the curve, right? That means that 50% of the data falls to the left of that, and 50% of the data falls to the right of it. Should be pretty easy. But if you score 1 standard deviation above mean, let's say you score right here on a test, that means that you have scored in the top 84%. Because it covered the 50 that's to the left of mean, plus the 34 between mean and mean plus 1 standard deviation.
Is this how they get like on the SAT?
Your percentiles? Yes, that is how your percentiles are calculated. And we have a section of this unit called percentiles. So we will be doing those. But you need to know if I say like, oh, that's 97.5% of the data, you go, ooh, yeah, that is 2 standard deviations above mean. You have to know that kind of thing. Or if I just say, what, 34% of the data, 16% of the data? Yeah, 16% of the data would be right here and to the left. You notice everything I'm talking about is to the left?
Yeah.
Okay. Again, we're talking a lot about to the left. Our calculators can all go to the left. Some of us have the newest operating system on our graphing calculators, and they can go to the right. And even better than going to the right, they can actually go between 2 values. But everybody's has the ability to go to the left. So when I teach this stuff, I will be teaching as if I can only go left. I'm pretty sure that my program can do left, right, and center. I'm going to pretend it only goes left because some of us have older operating systems, okay? All right. So you were supposed to notice that 68 and change percent is between 1 standard deviation up or down. So mu plus or minus 1 sigma. Roughly 95% is plus or minus 2 standard deviations. And then 99.74% is between plus or minus 3 standard deviations. And that is why we don't have any number for 4 standard deviations, because technically plus or minus 4 standard deviations should cover 99.999999% of the data, something stupid like that. Did any of you ever have to use the normal curve probability tables in Algebra 2 Honors? You didn't, did you? Did any of you get to the normal stuff in Algebra 2 Honors? Of course not. Because how would you? There's no way to get that far. Well, anyway, when we had an Algebra 2 FSA, we were expected to teach this kind of stuff to them. There used to be an Algebra 2 FSA. I said used to be.
I know, but like, when was that?
Like 3 years ago. Your freshman year was the last one.
Oh, Why are they stopping?
But I took Algebra 2 freshman year. I was taking FSA.
Was it? Maybe it was 4 years ago? I don't remember. All I know is that the thing was ridiculously hard. Only 40% of the state could pass it, and you only needed a 23% to pass it.
Oh, that's rough.
Our freshman year was the first year they got rid of it.
Was that the first year it didn't exist?
Yeah.
Wow, that test was hard. I mean, I would walk by it, look at questions, and go, holy crap, that's a hard question. I mean, it was rough. That was a stout exam, let me tell you. No, you didn't have to pass it. They tried to make it that you couldn't graduate until you passed that test too. I was like, no one's ever going to graduate. I was like, there's no way. That test is impossible for most people. Like, that test is ridiculously hard. Well, anyway, here you go. So plus or minus, well, the point I was getting at was the sheet they gave you. If you ever look at these old probability normal distribution tables, they don't go past. They don't even go up to 4 standard deviations. They give you like 3.99 standard deviations above and below mean. That's because statistically 4 standard deviations is impossible. Can you do it? Yeah, you can get numbers for it, but you need so many decimal places to represent it, it's just ridiculous. The chest measurements of 18-year-old male footballers, IB, talking about soccer players, okay, are normally distributed with a mean of 97 centimeters and a standard deviation of 8 centimeters. Okay, so we have mu, it's 95, and sigma is 8. This is important. It says find the percentage of footballers, what a weird thing to say. Find the percentage of footballers with chest measurements between 87 and 103. Okay. You would be surprised how often drawing a bell curve, 1, helps, and 2, get you some points. So here's A. So let's draw ourselves a quick little bell curve. It doesn't need to be perfect. We're not artists here. A bell curve. Yay! We have mean right down the middle at 95. We've been asked to go down to 87 and up to 103. So here's 87. Here's 103. I did my best to be symmetric. Because what I'd like you to see is the distance between my red number and my green numbers is 8. You see that?
Yeah.
8 is significant because that's a standard deviation. This 103 is plus 1 sigma, and that looks like plus 10, but that's plus 1 sigma. And this 87 is minus 1 sigma. So the question is asking you to find the percentage of data that shades. Well, how much data falls between plus or minus 1 standard deviation? Roughly 68%. It's roughly 68% because both sides represent 1 standard deviation away from mean, which is about 34%. Oh, and I guess this was a I. Boop. So here we have a double I. Again, drawing a bell curve.
They're not gonna dock you for like not saying 64 point like.
No. And I don't like that bell curve. I'm just gonna draw a little better. No, they're not gonna be too particular about the decimals for something like that. And to be honest with you, yes, I've seen some questions where you needed to know that 34%, but it was done in a slightly different way, so you didn't have to give that answer. You needed to understand. I think they said like, oh, roughly 68% of the data was yada, 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 and the student was supposed to go, oh, that's plus or minus 1 standard deviation. You know, it was done that way, so you had to realize that that's what that number represented, not that you had to produce that number.
Yeah.
It was more of an understanding thing. But yeah, or if we go like, oh, that person's roughly 84%, they go, oh, that's 2 standard deviations above mean. You know, things like that. It's supposed to be something you just understand.
Okay.
Right there, I'm drawing the same picture, 95 right there. But now my two numbers are 103 and 111. Oh, okay, well, 103 and 111. We've been asked to figure out how much data falls between these two green lines. That's what we've been asked to find out. Well, the 103 hasn't changed. It is still plus 1 standard deviation, so that's plus 1 sigma. And then 111 is actually plus 2 sigmas. So we just need to know, it's not a 10, it's 1 sigma. Yeah, I actually said that. Yeah, we just need to know, according to the classic numbers, how much falls right there. And you can use a pretty number, at roughly 13.5%. Right, is it 13.5? 6 something? Yeah, it's about 13.5.
2.59.
Yeah, you just call it about 13.5. You can get away with saying things like that. So yeah, this is about 13.5%, or 13.59 technically, but about 13.5%. Again, you need to know those numbers, but not down to the hundredth of a decimal. You just need to understand if someone says you've covered, what is 84 plus 13, like 97.5%, your job is to go, oh, that's all the way up to 2 standard deviations above mean. It's just something like that. You just have to know those numbers. You don't have to be able to reproduce them. You know what I'm saying? Cool. B says find the probability that the chest measurement of a randomly chosen football player is between 87 and 111. Oh. Okay. Well, that's not too bad. I just said that the 13.5-ish is good enough. It's a pretty enough number. Yeah. Part B. Huh. Part B, same bell curve, because again, you'd be shocked how often drawing the bell curve gets you a method mark.
Really?
Yes. So I do it every time because you never know when it's going to give you a point. So I'm like, okay, bell curve. Like drawing the bell curve is like, oh, student realized that it was a normal distribution. Bingo. They just got an R point, you know. And then this, I was supposed to go all the way up to 111. So how would we do this? Well, the first thing we did in AI was we found 87 to 103, right? We found that the 87 to 103 was about 68%. And we found that the, different color, how about pink, between 103 and 111 was about 13.5%. So what's the probability it falls between 87 and 111? About 81.5%. We literally just added the orange and pink number. That's it. It's that easy. No. Mm-mm. We haven't.
We've done stuff under the curve.
Yeah, we've done stuff under curves, but not this. So that was B. C. Find the value of K such that approximately 16% of measurements are below it. So last one, put right here. C. It says are below it, so approximately 16% are below it. Oh, I'm so bad at drawing bell curves. It's ridiculous. Here's my 95. And it says that roughly 16% is below some K value. Well, there's 50% below 95, right? So if I said 16% is below my number, I am to the far left of 95. Does that make sense? Because that number's smaller than 50. So I'm over here somewhere. Picture not drawn to scale because I don't actually know. And we did know that it's a K value. But what we know is that that shaded area represents about 16%. So what I need to know is what represents about 16% to the left? Well, one standard deviation to the left would be 50% minus 34%. Oh, that's one standard deviation left of mean. Because between 1 and 2, between one standard deviation left and right represents 34% on either side. So if here's 50, to the left of that is 50, and then this area is 34, to the left of this must be 16, because 16 and 34 makes 50. So that K value is minus 1 standard deviation. That K value must be mean minus 1 standard deviation, or 95 minus 8, which is 88 centimeters. No, sorry, I can do math. Sorry. 87. There you go. Yeah, that's what K is. Yep. K must be the number that is 1 standard deviation below mean. And that is your introduction to the normal distribution.